Right. Hello. Let's start then. All right. Hello and welcome to this talk. So I will be talking about how we brought our space combat shooter Chorus to a wide range of different platforms. That means I will be talking about how we polished and optimized the game in order for it to ship it to a great reception. So my name is Johannes. I'm a technical director at Fish Labs, based in northern Germany, Hamburg. And yeah, what I have to say first maybe is that this very much was a team effort. So lots of different people contributed to all the awesome things that we did. Obviously, I'm just the one who has the honor today to talk about this and tell you about all the cool stuff that we did. So before we go any further, let's take a quick look at what Chorus looks like so that you have a couple of images in your head while we go deeper and talk more about it. So it's a space combat shooter. Like the gist of it is that you fly around, you shoot stuff. Of course, we also have a story and cutscenes and all of that nice stuff in the background. But the important part is that this is a fast-paced game. And in order for this to feel good, in order for you to be able to succeed, and in order for this to be fun, it is important that we have a high frame rate and that we have a stable frame rate, and that that the game performs well, so that it feels good. All right, so what will we be talking about today? Let's get a bit of background information out of the way first, and then there are three main ingredients that we need to talk about. The first one being processes. So we need to organize around making this game run well on all the platforms that we want to ship on. The second thing is that we need to measure. We need to find our performance issues so that we know what we need to do, which is then the third part, the juicy bit of the presentation, where we go in and actually optimize stuff. All right, so the background information, a little bit of history. So Fish Labs has a history of making mobile games, and that's where we were in 2017 when we decided to pivot and change it around, and we decided to only do PC and console games moving forward. So we took a look at what was out there in 2017, and what we saw is pretty much this, right? PS4, PS4 Pro, Xbox One, Xbox One X, and your RGB-powered PC is what we saw, so we decided to ship our game for these platforms. However, over the course of the production, more platforms showed up, right? So you have the Generation 9 consoles, Xbox Series X, Series S, as well as PlayStation 5, that we also decided to ship the game on. But we also decided to support cloud gaming platforms like Stadia, which you know about. It's Fate now. And also Amazon Luna. So this is like then the range of platforms that we ended up shipping the game on, so quite a couple of platforms that we needed to support. In terms of technology, makes sense that I'm here today. So we shipped the game on Unreal Engine 426.1, but it's very much not a vanilla engine. So we backported lots of changes from 427 as well as Unreal Engine 5, but we also did quite a few custom engine modifications ourselves. So we very much optimized the engine for our specific use case. And more as a bit of background information, we also used some middleware like Bing, Fmod, Makuna for 3D navigation, but those are not going to be playing a big role today. So let's talk about challenges. And of course, you could ask me, well, Johannes, doesn't every game project have its challenges? And I very much would agree with that. But how is Chorus special in this regard? And the first one is the huge scale that we have. So spaceships obviously tend to be kind of fast. So in order for you to be able to traverse anything at all, we needed to build these super large locations that you can travel around in, so that you actually have some space, basically, that you can cover and fly around in. The next one is what we call semi-open world. So the game is not open world in the sense that you can seamlessly travel from the beginning to the end of the game. But we have these large locations that you can seamlessly travel around in, and that require us to stream stuff in and out while you are doing so. And the last one is the wide range of different platforms that we wanted to ship this on. So lots of different hardware configurations, lot of different aspects that we needed to look out for. So when we looked into shipping the game, we looked at the performance as we had it, and we looked at one of the most heavy levels that we had, which we used a lot of times as a benchmark. It was called the Armada Strikes. And this is running on Xbox Series X, and you see the player is not even really engaging, but there's a lot of action going on here. And you see it's kind of running in the 40s of the FPS, so there's definitely quite a bit of work cut out for us there in order to make this run well, because in this case the target was 60 FPS. All right, so as an overview, here you have all our target platforms, and you can also see that we have different performance mode for each platform. So we have a quality mode where we have a lower frame rate, higher resolution, higher quality settings, but we also have the performance mode where we have higher frame rate, potentially lower resolution, potentially lower quality settings. Where the hardware supports it, we also have ray traced reflections in the game, and these, of course, also have different performance characteristics after all. You can see that PC is kind of special. To be honest, we didn't spend too much time optimizing for that. The goal was kind of to have it running at 30 FPS at like the recommended specs. Yeah. And then, of course, with whatever hardware configuration you have, you can take the resolution, the quality settings, as well the frame rate wherever you want to go, basically. What you can also see is that we have our lower-end platforms, PS4 and Xbox One, which unfortunately didn't get the performance mode, so we only have 30 FPS support there. All right, now that we talked about all of that stuff, let's get into optimizing this. And as I said, the first step is to organize around this, make sure that everybody is working on the right thing and that we are all pulling in the same direction. And yeah, so it's kind of hard to get a team photo together in times of COVID-19, so we kind of had to improvise here. It's also not the whole team. There were lots more people involved. But the point here is that we have all of these different platforms. We have all of these different performance modes. And then in addition to that, you have different levels and locations in which different missions take place. And all of this leads to having a lot of different combinations that you need to cover. So basically, everybody had to chip in, right? You have QA testers playing the game, making sure we have data that we can base our decisions on what we need to optimize. We had art, tech art, programming, audio, all doing the thing, making sure their stuff runs well. And of course, you have producing, making sure that everybody's working on the right thing and that we are working towards the right goal. So when is it time to optimize? And there's this kind of famous quote from Donald Knuth: premature optimization is the root of all evil. And it seems to tell you that, well, you can just do whatever you want and then worry about performance later, right? You can always go back, optimize it. But to be honest, I wouldn't really agree with that. And if you look closely at what he's trying to say, it is that premature micro-optimization is the root of all evil. So the idea is that you need to to design your stuff and architect your software or your however you're going to build your game in a way that it actually can perform well later on, that you are actually able to go in and optimize your game without having to refactor or rewrite the whole thing. So you have to choose the right design patterns, for example. You have to choose the right data structures up front so that you have a good baseline that you can later work against and actually improve the performance. So in our case, that meant that we always luckily had quite a few performance-minded people on the project, mostly from a tech art and programming background, so they always kept an eye on the performance, making sure that it's not too bad. And in practice, that meant keeping an eye on our low-end platforms, so the game was always playable on these. We never had a situation where it just wouldn't run on the low-end platforms. But we always had it playable. It may have been running at the tens of FPS, but we definitely had a baseline there where we were able to then go in and optimize more. So I would recommend that you schedule quite a bit of time for optimization. So in our case, we had a production of roughly 3.5 years, and we very much spent the last 6 months on optimization. Of course, there's also other stuff going on there. We had to make sure to hit all the certification requirements. We had to make sure everything works together. The game is actually fun, fix all the bugs, all of that stuff. But we also very much spend a lot of time during this period on optimization. And I think optimizing your game is even harder than fixing bugs because you don't know where you're going to be in the end, right? You don't know what is my performance going to be, how much will I even have to improve the performance in order to hit my targets. I don't even know upfront how long it will take to optimize one specific thing because you don't even know what the culprit might be, right? And then in addition to that, it's also very hard to say, is performance good enough or not, because you're most likely not going to be running at your target frame rate, say it's 60 FPS maybe, 100% of the time, but you have to make tough decisions like is running 95% of the time at 60 FPS, is that good enough or not? And you have to define all of this. So what was our workflow like when we were improving performance? And the first step very much was to optimize in isolation. So that means we took individual levels, individual spaceships, individual visual effects, individual UI widgets or screens, abilities, all of that stuff, and basically put it in an empty location and looked at the performance like that in order to get an impression of how well is this thing running. Then you can already see, right, if it's very bad, you don't even need to integrate it with the rest because you need to do some optimization upfront. But you can also do things like if you have two different NPC spaceships and they have wildly different performance characteristics, but they should be able to be used interchangeably, then of course there's something wrong, and you can already also go upfront and optimize this. The next step then is to integrate everything, and in our case, that was very much driven by missions. So because the missions force the player to engage in the actual gameplay, right? So the missions take place in some kind of location. The missions are what spawn enemy ships, for example, and that allow you to engage in combat, and you need to spawn projectiles and spawn explosions and all of that stuff. Measuring the integrated parts of all that make up the game was very much driven by missions. So there's a lot of manual playthroughs going on here. So our testers were playing the game a lot on all the different platforms and generating data for us that would then go into these performance dashboards that we will be taking a look a little bit later at. So based on these dashboards, we would then triage this data. And that means that basically producing would get together in a meeting with programming and tech art, and they would take a look at the dashboards and identify which are our worst performing missions, where do we need to actually look more deeply into and figure out how we can optimize this. Which would then be the next step, like profile in detail, find out what are the actual performance issues for a given mission, what needs to be done in order to improve this. And based on that, we would be able to generate tasks and then just simply execute these tasks, right? Optimize. Should be simple then, hopefully. All right. As I said, the next step is to measure, and we try to automate what we could here. And the first one very much being an example of measuring in isolation. So we had a completely automated Jenkins job that would build the game every night for all our target platforms, deploy it to the target platforms, and run the game in a special mode. And this mode would just load all our locations after another, and in each location we would have predefined positions where we would put the camera. And then look at the performance data, automatically record this, and this would then go into a dashboard like the one you can see here. So here you can see over time how a specific location's performance evolves over time per platform, basically. And this already gives you a lot of information, right? You can see, am I moving in the right direction? Are we actually improving performance, or was maybe something introduced that led to a performance regression? Or are we even like at the level of performance where we want to be? The next thing was also completely automated streaming performance report, where we would just also every night automatically load the different levels that we had in the game and then record how long loading in these levels would take. We were also able from there to drill down into the individual asset level and see how long does each level asset take to load. And based on this, we would be able to decide, okay, this asset takes super long to load. We need to optimize this and look into what's wrong here. Looking at the integrated parts, we had these large dashboards for all our missions on all platforms, basically. So here you can see the columns are individual platforms and the rows are our missions. And if you ignore the completely red columns where we don't have any data here, you can quickly see that, for example, the one mission is only running 41% of the time on the one platform at our performance targets. And you can quickly tell, okay, this is something maybe that we should be looking at. As I said earlier, lots of manual playing went into this, so we needed to have actual QA testers play the game and make sure they generate this data. And one important thing to watch out for there is that you always want to have up-to-date data, because otherwise you will just be basing your optimization decisions based on old data, right? So you might go in and optimize this one mission for the one specific platform, and in your, like, what you're seeing locally, you are improving performance, and then the next day you go and look at the dashboard we just saw earlier, you still see that the performance is bad, and then you might optimize more. And that's, of course, not what we want. We always want up-to-date data. So we had like coverage dashboards like this, where you can see when which mission was played on which platform. And we would use this to tell our testers basically, okay, well, you need to take another look at this mission on this platform, because we need more recent data so that we can actually base our decisions on data that is up to date. So what performance data did we actually look at? And it's very much the classics. So in Unreal, you can display them with stat unit graph. So this the time it takes the CPU on the game thread or the main thread to simulate your gameplay, basically. This also includes like physics and UI work, stuff like that. We also have the time it takes the CPU to run the draw or render thread. So these are the CPU side preparations for rendering, basically stuff like culling, generating draw calls, all of that stuff. And then you have the GPU time, so the time that it actually takes the graphics card to put your nice images on the screen and to render them. So these are the three main factors that we looked at in these dashboards. So from the dashboard we saw earlier, the overview of the different missions, we were able to drill down also to the level of individual, to an individual mission on a specific platform, and see how these data points evolve over time and where they are in terms of performance. So this already gives us a pretty good idea of where might a performance issue be. Like, is it on the GPU, is it on the CPU side, for example? And then we would have a good first idea of where we need to spend our time moving forward. But as I also said, we also very much needed to go in manually and profile in detail, right, in order to find out what our actual performance issues are. And for these, you can use tools like Unreal's Profiler, Unreal's Insights, for example, as well, right? Just make sure that you instrument your code properly. You have these macros, the cycle counter macros that you need to put wherever you think there's something performance heavy going on. So for example, for our new project, we already have the guideline that in each tick function, so anything that runs every frame, you need to put these cycle counter macros there, so that we have a baseline of things that we will can look at later when we have performance issues potentially. Sometimes these tools are not enough, and you also need to get out something more platform specific, like Microsoft's PIX, for example, and use that to drill down even deeper into what's going on with the performance. And sometimes, like what you see there, this is a bit more disconnected from what is actually going on in the editor or in the engine, but you can still make this connection and use the data you get from platform-specific tools as well in order to find out what your performance issues are. So my recommendation is that you should always, like, continuously measure and keep profiling. Of course, after you have optimized something, you need to go back and check if you actually improve performance or if you maybe accidentally made it even worse. So make sure to keep an eye on that. And also over the course of the project, you need to keep making sure that you are moving in the right direction, that you are improving performance, and that there's not someone checking in something that completely breaks everything and makes your performance go really bad. So keep an eye on that. All right, so now we come to the juicy part. Let's talk about actual optimizations that we did. Yeah, and the first question is, how do we scale across all of these different platforms? And the answer is pretty much in the picture already, because as our lead programmer said, a rising tide lifts all boats. So in our case, that means that if we optimize the game for one platform, it will most likely also improve the performance on all the other platforms. And for Chorus, that was very much true, because we don't have a lot of platform-specific content. So the platforms are mostly differentiated by different frame rates, different resolution, potentially different quality settings. But in general, it's the same game running on all of those platforms. So in our case, that specifically meant that we spent around 70% of our time on our low-end platforms, making sure the game runs well on Xbox One and PS4 in this case. And then the rest of the time, we also spent a bit on optimizing for the other platforms. But yeah, making sure it runs well on the low-end platforms also make sure that you have a good basis on your high-end platforms as well. So performance optimization touches everything, right? It touches your assets, it touches your game code, or also touches the engine code. And there's a lot of different things that we did, and I really cannot cover all of them today, but I will be trying to hopefully cover the most interesting ones. So I put some of the others I had to cut on this slide here, just so you know we also did more things. But yeah, we did a lot of different things. And also, we really went into the engine. And when we looked after shipping the game, I went to look into the engine. And what I found is that we did over 1,000 different individual modifications to the engine code. Of course, this is not all performance optimization. There's also lots of bug fixing and tweaks in there to like specialize the engine for our use case, but also definitely a big chunk of that was optimizations. All right, so I've categorized the different performance optimizations that we did into different categories. And the first one of these is doing it right, doing properly, using the tools that you have. And the first one very much is use the power of Unreal because it already gives you a lot of features and systems that you can use in order to improve your performance. So first off, you should definitely configure your device profiles and scalability settings properly for your game and for your target platform so that you have a basis that kind of runs well on these and that you can then from there go and optimize performance even further. I also like dynamic resolution a lot because it allows you to optimize and optimize and optimize. And if you run out of time, you can just switch on dynamic resolution. And as long as you're GPU bound, it will just hit your target frame rate afterwards, which I really like. And the good thing is also here that apparently players don't really seem to mind if we just drop our resolution a little bit. As long as you don't go too low with the resolution, it seems to be fine nowadays, and this seems to be an accepted feature for players. Another thing that we did is we manually translated lots of our blueprints to C++, and my recommendation would be anything that ticks, anything that runs every frame definitely needs to move over to C++, because on average we see like a 10x speed up when doing this. So as long when you have something computational heavy, you should definitely move that over to C++. And then there are other tools in the engine as well. One example being the significance manager, which allows you to lot things based on significance. So in practice, it's mostly loading based on distance to the camera. So for example, your particle systems or your sound effects, if they are too far away, you won't be able to hear them anyway. So you can just use the significance manager to switch off sound effects that are far away, for example. You can also use this for more gameplay-related things. So in Chorus, we have these ambient traffic ships that are moving on a spline, like in the background to make the world seem more alive. But these are just moving on a spline, and if they are far away, for example, we can just go and reduce their update frequency and just not update them as often. Also, as they are moving on a spline, they are not going to collide with anything, so we were able to just switch off collisions when they are far away, and then only when the player gets closer, we need to enable collisions again, because the player might bump into them and push them around, stuff like that. The next thing we needed to get right was level partitioning. So in Unreal 4, you still have the world composition system, which is different from Unreal 5, but we still had to deal with world composition. And here, what is being streamed in very much depends on the level boundaries. So you have all of these individual levels that make up your world, and here you can see in yellow the boundaries of these levels that basically decide if something needs to be streamed in. And the problem is, or that we had, was that these level boundaries are automatically derived from all the actors that are part of this level. And if you don't have correct level boundaries, they might end up being in the wrong place. So they might end up going right through a combat area. So while you are there fighting, doing lots of CPU heavy stuff, you also all of a sudden need to load some stuff or unload some stuff, and that would just then break the performance in our case. Or if your level boundaries are way too big, then you will run out of memory because you have all the stuff loaded at the same time. So as I said, by default, like the boundaries are derived from what is in the levels. So the fix was to use fixed level boundaries. Just for each level, we go, okay, these are these boundaries, and even if you have a level over here and you add an asteroid over here, we are not going to extend the boundaries. And the idea being that if someone places an asteroid, they will hopefully go and take a look if this is actually still being streamed in, if you go there. And then they realize it's not being streamed in, so they need to put their asteroid that's over here in a different level, hopefully. in order to hit also the memory constraints of all of our platforms, we had to make sure that these level boundaries were as tight as possible. So we actually had technical artists going in there and manually creating lots for our levels in a lot of cases, so that they would look good so that you can still move pretty close to them without them looking bad, and then only at the last second basically swapping in the actual geometry with a nice dithering effect. All right, now we talked about what we need to do, tools that we should use, how we should do it, but there's also a couple of things that you should avoid, that you shouldn't be doing. So let's take a look at that. And one of our examples is overlap events. So here you see a screenshot from the documentation we had for the project, and the lower red line is, in this case, the budget for the frame. This was a 30 FPS target. And then the red line in the middle is overlap events alone. So our problem was that overlap events would take up to 50 milliseconds per frame. The thing with overlap events is they are kind of convenient. You can just, if something overlaps, right, just trigger whatever gameplay logic you want, and they give you a lot of detailed information. They tell you where is the overlap happening, what primitive is involved here, and all of this stuff. But they are kind of expensive. So we need to solve this problem, and we came up with a couple of different solutions. The first one is that we can avoid moving because overlap events respond to moving. But that's going to be a pretty boring game if nothing is moving, right? So you can kind of reduce how often you set the position if you accumulate position updates, for example, for one specific actor. You can also get around by reducing the number of scene components you have, for example. You can also reduce the number of updates to positions that you need to do. But in general, there's like a limited limited progress that we can make with avoiding moving. What we also did is we went into the engine and disabled overlap events by default, so that you have to specifically go in there and say, okay, I need overlap events, I need to enable them, so that you make a conscious decision about this, that you actually need them. And then most of the time you don't need this detailed information. You don't need to know what is overlapping where, but in most of the cases you just want to know if the player is close enough to one thing and then trigger something. So that's why we implemented like custom trigger components and actors in order for people to use this for their gameplay functionality. And then if you really need this detailed information that overlap events give you, you can still go in and call a function like sphere overlap actors and on demand basically get this information and do the overlap check. Another thing we needed to avoid was garbage collection. So Unreal has this nice and convenient garbage collector, but our problem was that no matter what we did, it always caused us performance issues. And as we can't get rid of the garbage collector, we can just work on improving this, right? So you need to reduce the number of objects that the garbage collector needs to consider. So you can tweak some values in the engine configuration for that, for example. But you should also be using this clustering feature, which allows you to load in a complete level as one garbage cluster, so that the engine doesn't need to look at individual actors, objects in this level, but just treats the whole thing as one garbage object, basically. Just be aware that then if you attach an actor to something in this level, you will also have to add your actor to this cluster, because otherwise you end up with dangling references, and we don't want that. Something that was more specific to our case is that we have these large locations made up from different levels, and what would happen potentially is that different or multiple levels would end up being unloaded at the same time. And the engine, by default, every time a level finishes unloading, will run the garbage collector. So that, in our case, could lead to one level finishes unloading, then the garbage collector would run, the next level would finish unloading, garbage collector would run again, and so on, so that we would end up with multiple frames of bad performance. So we went in there into the engine, and what we did is we implemented it so that we now defer this garbage collection run for up to 2 seconds after a level has finished unloading, so that we can potentially have multiple levels finish unloading and then just run the garbage collector once. Because the garbage collection run is not going to be a lot more expensive. If it finds more garbage, it still needs to go through all the objects. And then we also moved this call to fmemory trim, which tells a couple of systems now would be a good time to free up some memory. We also moved that to a subsequent frame because it made the garbage collection frame just a little bit longer, so we could just schedule that for the next frame as well. All right, the next thing to avoid is hindering asynchronous loading. So first off, of course, you should never load anything synchronously while you are in action gameplay, right? Always request stuff asynchronously, go and do something else, check if your thing is done, and only then use it if it's ready now. However, the problem that we found is that there are some functions in the engine that actually wait for everything that is being loaded asynchronously to finish. And one of these where this makes sense is obviously the synchronous loading. So if you load something synchronously, it will also just asynchronously request a thing and will wait for it automatically. So that means even if you're loading something small synchronously, everything big that was requested asynchronously before has to finish first because before the engine gets to your small thing that you are waiting for. But there are also other functions in the engine that surprised us that they are actually flushing this async loading queue. So for example, renaming an actor or removing the last component of an actor will just wait for everything to finish loading asynchronously for some reason. Just something we had to be aware of in order to avoid this performance pitfall. All right, next category is throttling. And the idea here being that you distribute the work over multiple frames, right? So you don't do all the work when you can do it, but that you distribute it over multiple frames. That means it might take longer to finish, but you get a smoother frame rate in return, which feels a lot nicer to play with. So here on the side, you see, like for one of the locations, a couple of the levels that are involved with this one location, and you see we have all of these different levels, like for audio, for gameplay, for lighting, for missions, for geometry, lots of different levels. And as I said earlier, the level boundaries might potentially overlap, so we could run into the problem, like with the unloading, that multiple levels would be loaded at the same time. And what we found is that the engine only has one budget per level when streaming stuff in. So it potentially, loads all the data for the one level and exceeds the budget. And then it will have a fresh budget in the same frame for the next level and will keep loading on that, which obviously makes your one frame where you're streaming in multiple levels take way too long. And once you have found that out, the solution is kind of straightforward. You just go in there and change it so that you have a shared budget that all the levels being streamed in at the moment take the time out of, so that you don't basically have multiple budgets for one frame, but that you only have one. Another thing that we found was that the game thread would do its loading and then just push all the work that the render thread needs to do, right? Loading of textures, stuff like that, pushes all of that to the render thread without any regard for how much work can the render thread accomplish in one frame. And the render thread also doesn't have a budget for this. So this would potentially mean that the render thread would be doing way too much work during one frame. So we went in there and implemented on the render resources this new function, which is quite a mouthful, get estimated post-load RT cost, which implements a heuristic. How long is it going to take to load this render resource on the render thread, right? For example, like if you have a large texture of a couple of megabytes, that's going to take way longer than just a tiny 16 by 16 pixels image, for example. So we would use this on the game thread to steer how much work are we sending to the render thread during the current frame, so that the render thread wouldn't go overboard in terms of budget. And then we had this budget on the game thread to steer the work that gets sent to the render thread. Another example being what we call incremental initialization. So when we spawn stuff or when we stream stuff in, actors need to get initialized, right? And actors contain several components, and all of these need to get initialized as well. And what we found is that we had pretty heavy components, pretty heavy actors that would get initialized, and the engine has a budget for this, right? So it initializes an actor, checks the budget, then initializes the next actor, checks the budget, and so on. However, in some cases, this wasn't fine-grained enough for us, so that one actor would already take too long, the second actor, so we have one actor being completely initialized, and then we check the budget, and then we have the next actor already taking so long that this is too long for our frame, for example. So we went in there and changed this so that we have more fine-grained control, that we basically can go and cut this off after each component, that we check the budget for initialization, after each component, and that way have, again, a smoother frame rate, which really had a huge impact, especially in combat situations when we had to spawn enemies, right? When we had to spawn explosions, when we had to spawn visual effects, projectiles, all of this stuff. And we were already busy on the CPU doing all the combat simulation. We definitely only had like a small window to spawn stuff in addition to that. And this is where this made a huge difference. All right, next up is rewriting or maybe refactoring after all, because sometimes you make the wrong decisions in the beginning and you have to go back and reconsider them and maybe find a different solution for something that didn't work out in terms of performance. In our case, one of the examples are our radar target markers. So kind of some of them are difficult to see, but for example, you see the red square there, but I've also highlighted the others. So the point is that we have quite a few of these different target markers, and of course they're also more visible when they're actually in motion, but they tell you important stuff like, okay, there's something here where you can go, which might be interesting to you. So our problem was that we had lots of these markers and we were using UMG widgets for these, and that ended up being way too slow. So we looked into how we could improve this, and yeah, we were using this UI particle system plugin from the marketplace already. So we just went ahead and made our target markers particles, basically. So now they are rendered through this particle system. Of course, there's no particle simulation going on. Like we just go and set the position. Okay, you need to be here in order for the player to be able to tell this is where I can go. But otherwise, there is no simulation going on. But we were still able to have have the target markers look different based on different sections on the particle timeline. And this gave us a nice 3 to 4 times speed up for our target markers, which was definitely very welcome. Another thing we had to reconsider were the explosions that we had, because for one, they were expensive to simulate, and the other thing was that they caused because we have these little debris particles in there, which all were one individual draw call, and and they were expensive to simulate because they were the one thing that were actually using physics in the game. All the rest is just fake, implemented manually by us, basically. So they were actually using physics. And the solution that we came up with is that we use a skeletal mesh for our explosions. So now all the different debris parts are actually just bones that we can move around individually, but we still only have one draw call for all of this, which is quite nice. And as they are bones now, we don't have any physics anymore, so we just went ahead and basically implemented the simulation manually as well, just faking it. So the performance is a lot better for that. All right. I mentioned micro-optimization in the beginning, and at some point you come to the point that you need to do this after all, so you need to worry about your instruction level performance, right? You need to worry about things, okay, I do the cheap checks first, check the pointer first, then do the cast, and then call a more expensive function potentially. You need to worry about maybe I shouldn't use cast because it looks at the whole type hierarchy. Maybe I should just use exact cast, which just looks at one specific type. Or maybe even go further and just use flags or enums to identify types. And of course, there's a lot more of these things, but your profiler will tell you how you can improve the performance on an instruction level for the code that you wrote. And now the question is, did all of this work pay off, right? That's the important question now. And I'm happy to say it very much did. So if we look at the benchmark we had from the beginning again, now we have a very stable 60F running on Xbox Series X here. And luckily, the press also very much agrees. So we have a solid 60 FPS. We have plays incredibly smooth, runs incredibly well on PC, no drops in frame rate, and just keeps on going, silky smooth game. So of course, if you worked on the game, this reads very nicely. Yeah, we also won the award for Best German Game at the German Computer Games Awards. And well, this is from a forum post, but it says the game feels like it runs at a 60 million FPS. And of course, while that was our target, we didn't quite get there. But of course, still nice that people noticed this. All right, So let's wrap this up. If you have been asleep the last 40 minutes, here are your 3 major takeaways. The first one is you should focus on your low-end platforms, make sure it runs well on those, because that will most likely also benefit your high-end platforms. The second one, you should generate lots of data that you can base your performance optimizations decisions on, so that you actually know that you're optimizing the right thing. And the third one is that you should leverage your engine, use the tools that you have, but also don't be afraid to go in there and change the engine to really specialize it for your specific use case, because there's definitely most likely some room that you can gain there in order to make this the engine for your specific game. All right, that's it. Thank you, and if there are questions.